All right, let's move on. Hash functions. So we now understand symmetric algorithms, asymmetric algorithms, the challenges and benefits of both of them. Then we have hashing algorithms. So hashing algorithms. Why do we need hash functions or hashing algorithms? What is their purpose? Let me do a quick time check. Oh, it's already 8. Okay, I think I will not be able to cover PKI, but let's quickly go through hash functions first. So, hashing algorithms, let's say you are sending a message from user A. Let's say user A is sending a message to user B, and the message gets corrupted in between. Maybe there is maybe the cable is faulty, or maybe there is some excess power in the cable, or there is some other problem because of which the message gets corrupted. Now, how will the user B get to know about it? User B will get to know about it by using methods like CRC, right? If you've heard of CRC, CRC stands for cyclic redundancy check, or there is something called parity bits as well. So there are mechanisms in place to detect those that kind of corruption of data, CRCs or parity bits. But where hash functions come into play is if somebody deliberately modifies the message on the way, then how do you detect it? So CRCs and parity bits can only be used for unintentional modifications, like a power fluctuation maybe, or a faulty cable. But if somebody deliberately makes changes in the message, then we use hashing algorithms. All right, hash functions or hash algorithms, it's one and the same thing. So as it says here, hash functions are needed to detect unauthorized modifications to data, whether it is intentional or unintentional. All right. Now let me explain how that works, and let's go back to the drawing board. So we have two users again, user A and user B. All right. Now user A wants to send a message. Let's say the message is ABC123. This is the plain text message that needs to be sent across to user B. Now user A wants to make sure that when user B receives the message, user B can confirm that the message was not altered by anybody on the way, whether intentionally or unintentionally. So what user A can do is user A can use a hash function. Hash functions are MD5 or, for example, SHA. So it can use any hash function, whatever the user A wants. So the way it works is the hash function will take this plain text message. It will run it through the hash function, hash algorithm, and it will give it a value, which is called a hashed output, a hashed value, or it is also known as message digest. All right. And this message digest is of a fixed length. All right. For example, this could give a hashed value of 128 bits, depending on what algorithm is used. It will always generate a fixed length output, no matter how long or how short the message is. It could be variable, but this output will always be fixed length. All right. So this message is sent through the hash function, and the output is a fixed length message digest. Now this message digest could be something like, let's say it gives a value of 10111. This is the MD, message digest. Now this message digest is appended to the original message, which is 101111. And then this message is sent across to user B. Now user B gets this. So user B gets the message and the MD value as well, which is 101111. Now user B will again run the same message, just this part here, through the same hashing function, and user B will also get a MD value, right? So if the user B also runs the same hash function as the sender had applied, then the value should be the same. So user B will also get a hashed output, which should be 101111. Then user B will compare its own hashed value, message digest, with the one that was sent by them in the message. And if they are the same, then that means the message was not modified. But if, let's say, there is an attacker who took hold of the message and modified it, and added, let's say maybe let's say this was ABCD, ABC123, right? Now let's say the user, some attacker converted it to XYZ123. Now when user B runs the hashing algorithm on it, the output would be different because the message is different. So it will be 101110011. And now these two don't match. So this will tell user B that, hey, the hash values are not matching. That means the message that was sent by user A has been altered, either intentionally or unintentionally, and it will discard the message. And it will send a message back to user A saying that, hey, I'm discarding the message. The hash values are not matching. So send the message again. So that is the purpose of hash. It provides you integrity. All right. Integrity means to ensure the ability to confirm that the message is correct, that the information is correct. All right. So it is able to, so hashing functions provide you integrity, the ability to check whether the message is correct or not. All right. And this is how it performs it, how it does it. Let's go back to the mind map. So hash algorithms take a message and produce a fixed length value called hash value or message digest. So it always takes a variable length message, and the output is always a fixed length value. If the sender wants to ensure that any modification in the original message should get detected, the sender can, I just explained this to you. I don't have to read it again. Next one is hashing algorithm is publicly known. Its secrecy comes from the fact that it is one way. Now, what it means is that this algorithm that was applied here on this message, it is publicly known. There is no secrecy in this algorithm. So if the user A is applying MD5, everyone knows how MD5 works. The secrecy here, and there is no key involved here as well. But why do we not need a key when this hashing algorithm is public? We do not need a key here because there is no reversal happening here. So the thing is, this hash function is one way, which means that you can only perform it in one direction. So ABC123 is the message. When it is run through a hashing function like MD5 or SHA, it will return you a message digest, which is 101111, and that's it. You can't reverse the process. So you can't look at this message digest and somehow arrive at the message which is ABC123. That is not possible at all because hash functions are one way. And because they are one way, you don't need any secrecy there. The job of hashing function is to just calculate message digest, and then the other party will also calculate that message digest. And if they are the same, then that's it. That is the job of hashing function, right? You don't have to reverse it. And that is why we don't need a key here. All right. So it is one way. And then a strong hashing algorithm should not produce the same hash for two messages, right? Because then there would be problems. So if let's say ABC123 message produced a hash of 101111, and if the attacker sends a message, alters the message, which is XYZ123, and if that also somehow produced the same hash, which is 101111, then the user B will not be able to detect the change, right? So no two messages should produce the same hash. In case two different messages produce the same hash, then that is called a collision, which should not happen. Okay, when two different messages produce the same hash output, it is called a collision. So ideally, all the hashing algorithms should be collision free. Okay. Now, there is something called HMAC, hashed message authentication code. All right. Now, let's say why do we need HMAC, or what could happen here? Let's take a look at this example here. Let me explain it on this page here. So let's say user A wants to send a message ABC123 to user B. User A runs it through the hashing algorithm, and the output that is derived is 101111. It is appended to this original message and sent across. Now there is an attacker, okay, on the way, and the attacker captures this message, which includes the original message as well as the hashed output, the message digest. The attacker changes the message from ABC123 to XYZ123. All right. And the attacker removes this MD as well. because the attacker has that ability. So attacker removes that MD, message digest, and it calculates a new MD using the same algorithm like MD5, for example, and it gives it output, let's say 10110011, and it appends this new MD 10110011 and sends it to user B. Now user B receives this message XYZ123 with this new hash output 10110011. User B applies the same hashing algorithm and arrives at certain output. It compares the two, 10110011, and user B had also gotten the same output, 10110011. Both are same. So user B accepts this message, this one, right? And there is every possibility that this could happen because the attacker did not just modify the message, the attacker modified the hash value as well. And that is why user B was not able to detect this change. And to avoid these kind of scenarios, these kind of attacks, we have a modified version of hashing functions, which is called HMAC, hashed message authentication code. So the way it works is, again, let's take user A and user B. User A has a message ABC123, which needs to be sent to user B. So user A says, all right, I'm going to use a hashing function to make sure that user B can detect any changes. But now user A is smarter than before. So user A says, all right, I'm not going to use a regular hash function. I'm going to use HMAC. All right. With HMAC, what it does is, so user A says, all right, along with, I'm not going to apply the hash function on just the message. I'm going to first add a secret key to the message. So it will add a secret key to the message. For example, the secret key could be, let's say, 111. All right. So it will say, let me append this key to the beginning or wherever. This is just an example. So it says, all right, I will append this key, and now I will apply hash on this complete new message. All right. Now hashing will be applied, or HMAC, and now a new output will be received, which is, let's say, 101011. All right. And now this will be appended. This is the message digest. So this message digest will be appended to the original message 101011 and sent to user B. All right. Now user B receives this message ABC123 along with the hashed output 101011. And now user B says, all right, let me confirm if it is correct or not. So user B takes the message ABC123, and before it runs it through the hashing algorithm, it again appends the same key that was appended by user A. So the key is not actually sent here. All right. The key was just used here for the purposes of HMAC function. Once it is used, it is then kept with user A. But user B somehow has to have the same key. All right. So they should have already somehow exchanged these keys securely. So user B says, all right, I'm also going to append the same key here and then apply the HMAC function. So it will get a value 101011. If it will compare it with this one, and if they are the same, that means the message is accepted. It is correct. All right. Now let's go back to that attacker scenario. If there is an attacker here who receives the message and alters it from ABC123 to XYZ123, and it also applies a new hashed output, let's say 001111. Now, the attacker does not have this key, this secret key, right? Because this is a secret key, which was only with user A and user B. So now when user B receives this message, user B will append the secret key to this message and apply the hashing algorithm. And it will get a different output. For example, it could get, let's say, it will get 001111, which was appended by it will get something else because this value was calculated based on just this message. But now user B has appended a key as well, which will give a different output. For example, 110011, and it will not match with the received HMAC. So this message will be rejected. So this is the benefit of using HMAC, so that even if an attacker changes the message and changes the hashed output as well, the receiver will still be able to detect it because they have the sender and the receiver are using a key in the overall process. All right.